Cheers, everyone. Happy E-Days. If you've got anything, she's got a lot to provide.
I passed more out. Don't worry.
Okay. I am being careful. How many of you checked your grade on the last quiz? Don't worry. If you were here, there they are. You'll be fine, trust me. At any rate, me and Madison had a long conversation about it, and those are the results. Okay. Woo! There's something really long about this lecture. Lots of good stuff, but it's extremely, it's like it's extenuated and super long. Okay. All right. So we're going to start with something which is not going to look familiar, but then will be incredibly familiar. So, let me start with a little story about a space that you have not seen before. Okay? So consider the space described by the following metric: minus dt squared plus dr squared plus r squared plus b squared d theta squared plus sine squared theta d phi squared. Okay? Where this b is just a constant, nothing weird. All right? Now let's put the ranges on all of these. So t can run from minus infinity to infinity. R goes from 0 to infinity. Theta goes from 0 to pi. And phi goes from 0 to 2 pi. Okay? Now, I would like to make a few observations about this geometry, and then we're going to do something with it. Okay? So first of all, note no time dependence. Okay? It obviously is a metric that involves time, but there's no time dependence in it. Hopefully, do you all understand what I mean when I look at a metric and I say it does not depend on a particular coordinate? I'm looking at the coefficient functions and asking, does anything depend on t? And nothing depends on t. Okay? So this, of course, means that it's stationary. And moreover, there's no dt dxi terms. So this means that it is Sam. Sam.
Static?
Yeah, that means it's static. Good. Okay, so this is a pretty simple geometry. All right? For r goes to infinity, what do you think this describes? Any takers? Let me get to the ones I haven't. Nick. Nick? No Nick. Oh man, I'm going back to the Sean.
Would it be flat space?
Yeah, for r equals infinity, this goes to flat space. Okay, it just goes to flat space. And that's just because when r is infinity, if b is finite, this term just becomes r squared. Okay? And then last but not least, and this might or might not be obvious, this is S2 foliated. Okay? That is, for a fixed r and t, theta and phi sweep out a two-sphere. Okay? Now that's foliation that's going to be important in just a moment. Right? Now, since this metric is time independent and static, in fact, there's no real reason to include the time part of the story. Because the time part of the story is just like, I'm going to live in time. We're drawing pictures and shit, all that's static anyway. So let's just ignore the time dimension for a moment. And that is, of course, going to reduce us to ds squared is dr squared plus r squared plus b squared d theta squared plus cosine squared theta dp squared. Okay? And this is now a three-dimensional spatial geometry. So it's not a time, it's not a space-time anymore, it's just a space. Okay? And unfortunately, since it's a 3D geometry, it's very hard to draw. I mean, I can draw a 3D space by going, this is the coordinates, but you're all going to look at that and go, he's talking about R3. It's really hard to draw a curved three-dimensional geometry. Or if it's curved, I don't know what it is. So what we're going to do is we're going to reduce this to a two-dimensional geometry. And in order to do this, we are going to take the spheres. So what we're going to do is we're going to fix theta to be pi over 2. So what this does is it takes all of the two-dimensional spheres and it replaces them with a circle. Okay? So I'm going to draw circles in illustrating this geometry, but you must realize that the original version of the geometry replaces every circle with a two-dimensional sphere. Yes?
I was confused why the sine squared phi turned into cosine squared dv.
Oh shoot, yeah, because I'm just being stupid.
Okay.
Yeah, no, I'm just being stupid. Okay. Now, if we do this, then our two-dimensional version of this geometry becomes ds squared is dr squared plus r squared plus b squared d phi squared. Okay? So now we've got a two-dimensional geometry which we might be able to illustrate. And in order to do this, what we first of all realize is that our 2D metric is in polar type coordinates. Okay, they kind of look like polar coordinates. And they are circularly symmetric because it only depends on r. There's no phi dependence in there. Okay, so there's a circular symmetry to this geometry. And now what we're going to do is to understand this, we are going to take this two-dimensional geometry and we're going to embed it in 3 dimensions. So we're going to put it back into 3 dimensions, but we're not going to make it a 3-dimensional geometry. Rather, we're going to have this 2-dimensional geometry live in 3 dimensions, but it will be non-trivially embedded. So the curvature of this thing, you will realize based on the shape of this 2-dimensional surface in 3 dimensions. Okay? I want to stress, this is a 3-dimensional geometry. This is a 2-dimensional geometry, which we are going to embed in a 3-dimensional geometry. We're going to draw a surface in 3 dimensions. This is a 3-dimensional surface, which is freaking hard to draw. That's why I made it a 2-dimensional surface. Okay? Good. All right. So let's see how this works. So let's go to R3 with coordinates z, rho, and psi. And these are just going to be cylindrical coordinates. So you realize the cylindrical coordinates, this is the axial coordinate, this is the radial coordinate, and this is the angular coordinate. Okay, this is typical cylindrical coordinates. And our ds squared in that coordinate system for the 3 dimensions is dz squared plus d rho squared plus rho squared d psi squared. Okay? This is just the metric of R3 using the cylindrical coordinates. Hopefully most of you should be somewhat familiar with this. And now what we're going to do is we're going to identify these coordinates with the embedding coordinates. So what we need is, we need z as a function of r and psi, or sorry, r and phi. We need rho as a function of r and phi, and we need psi as a function of r and phi. Okay? Now, one of these is super obvious how to do it. Which one? Z, that's the axial. So you guys know what. Okay, which of these is obvious?
Rho is a function of r and would just be r.
No. That's a good guess then. Come on, folks.
I don't know.
Would Z just be like Pythagorean theorem? We could do that.
Nope.
Is Z just Z?
Nope.
Is psi just our phi?
Yeah. If we take psi and we just make it equal to phi, then we replace that angle which goes from 0 to 2 pi by another angle which goes from 0 to 2 pi. Right? Nothing weird there. Okay? Because notice that's something simple about that, because this doesn't depend on phi and this doesn't depend on psi. So interchanging one for the other, there's nothing weird. Interchanging rho with r or something like that, that could actually screw things up. Okay? So now what we want to do, in order to get z of r and rho, oh, actually, sorry, we're going to do that, and we are going to assume that these definitions do not involve phi at all. So they're just going to be radially dependent. So in order to find those, what we can do is we can plug this in to the metric, and this is going to give us dz squared plus d rho squared. Hold on. No, I don't want to do that. I'm going to write this metric in terms of these functions. So this is going to be dz dr, and that's d not partial, dz dr squared, dr squared plus d rho dr squared, dr squared plus rho squared d phi squared. Okay, first of all, if you look at this, this should not be difficult. The dr squared here cancels the dr squared there. I know we're playing that slick, like, you know, the argument with which respect we're taking the derivative with respect to is the denominator. That's not exactly true, but we're going to treat it like it's true because, hey, we can. This dr squared cancels with that dr squared. That gives me dz squared. That's that term. Boom! That dr squared cancels with that dr squared. That gives me that term. Boom! That's the same term. Okay? However, notice this is now a two-dimensional metric because it's only got two coordinates, r and phi. Okay? So, what we can say is if rho squared equals r squared plus b squared, then this immediately implies that dp dr, or d rho dr, is r over the square root of r squared plus b squared. And dz dr squared plus d rho dr squared is one, exactly. Okay? Then what we have, and by the way, this guy is going to tell us that dz dr squared plus r squared over r squared plus b squared equals 1, which tells us that z of r is b times the inverse of the hyperbolic sine of r over b. Oh, goodness. Having chosen z of 0 to be 0. And I know I'm kind of skirting through this really quickly. This is not, I'm just doing the backbone stuff. I don't really care about these details. That's why I'm flying through them. Where I get to is what's important. So bear with me on this road trip. Okay? Yes. So I'll just skip the next step and actually write down how z depends on rho. So z depends on rho as b times the inverse of the hyperbolic sign of the inverse hyperbolic sign of the square root of rho squared over b squared minus 1. Okay? And then, of course, we have the metric. It's dr squared plus r squared plus b squared d phi squared. Okay, I've got all that crap on the board, but I'm really not that interested in it. What I'm really interested in is drawing this thing. Okay? So let's draw this space for a moment. And what it ends up looking like is as follows. So we have a vertical axis, which we can call the z over b axis. We have a horizontal axis, which we can call the rho over b axis. And then, what we know, of course, is that z of rho is b inverse hyperbolic sine of the square root of rho squared over b squared minus 1, and r is, of course, the square root of rho squared minus b squared. So if we plot this, what we find is the following. Okay? Where this point is illustrative of either rho equals b or r equals 0. Okay, now remember that to restore this to a three-dimensional geometry, we take every circle in this picture and we replace it by a two-sphere. You can immediately see why that would be difficult to draw, right? Now, here's the very important thing to observe about this space. First of all, it ends right here. Remember, the space that we started with had r going from 0 to infinity. And this space is illustrating that same range for r. R goes from 0 to infinity. It's just that the value in the embedding space of r equals 0 is a distance from 0 along rho. Okay? And this poses a problem for the following reason. This space is not geodesically complete. Now, what do I mean by that? Well, you know what a geodesic is, right? You got the geodesic equation, which incorporates the metric, okay? It actually incorporates the Christoffel connections. But if I pick a point and a starting direction, then I can solve the geodesic equation, and that will tell me the geodesic path, okay, with that as a boundary condition. Now, I should be able to draw the forward-going path by solving the geodesic equation, but I can also find the backward-going path, or the path where the object is coming from, okay? Well, some of these paths are going to look like that. They'll go off to infinity here, they'll go off to infinity here, and they'll be happy the whole way. Some of them might be in orbit, okay? But some of those paths will come from here, or actually from here. All right? So I can actually have a geodesic path. Maybe I start right here, my direction's that way, and the path goes off to infinity, but if I go backwards, it hits this ring where it stops. Because this space ends here. Okay? So, now I want you to notice. In normal R2, which is not the space we're working in here, in normal R2, R equals 0 is not a point of termination of geodesic paths, because in R2, if I pick a path, it's going to go straight through R equals 0 and keep going, okay? Here, though, because of the structure of this space, if you are backtracking to R equals 0, or if you just aim at R equals 0 and you go to R equals 0, you can't go further. You can't jump across this loop, okay? So what can we do to fix it?
Take the limit as b approaches 0.
We could do that. But the limit as b approaches 0, that's kind of lame. It's just making the whole space R4 or M4. What else can we do?
Could you create a copy on the bottom side?
We can do what is called a maximal extension of the space. That is, we can include a new branch of the space, defined in a very specific way, but which obviously cures that geodesic incompleteness. Because now this guy just continues. Okay? What is this space? It's a wormhole. It's a wormhole which connects what is ultimately something which is asymptotically flat space in 4 dimensions, it's infinite, to another copy of asymptotically flat 4-dimensional space. This is what is often called a bridge, and I'll just draw a quick picture of it. A bridge, like the Einstein-Rosen bridge, which was the first realization of this, basically takes a space which is infinite and flat and connects it via a wormhole to another copy of the similar space. Yes?
I don't want to go off on too much of a tangent, but what exactly is an Einstein-Rosen bridge? Can you just expand a little bit more on that?
So this is a geometry which is described by this metric. It is a geometry, so it's described, sorry, so I should say, in order to describe this geometry, what we need to do is we need to take this and change it to that. Everything else remains the same.
Oh, so that's the only difference.
It's definitely different. Normally with spherical polar coordinates, we only let r start at 0 and go to infinity. There's no going in the negative direction, because going in the negative direction is going in the same direction, but with theta equals pi.
Okay.
Okay, if I'm trying to, so if I'm coming out here, then I can go here by going the same radius, but at theta equals pi. Okay, I can't take theta as pi and go from here to here. Can't do that.
Yeah.
Okay? So this is a change in the range.
Okay.
Okay? But at any rate, what it's doing is it's taking 2 copies of flat space, and it's basically poking a hole in each of them and then smoothly connecting those 2 spaces. And the argument here is that this space, which we normally don't think of, can be a solution to Einstein's equations. Okay? And it's a better solution than this, because this was geodesically incomplete. This solution is geodesically complete. And I'm going to come back to that in a few minutes, and it's going to mean a lot. That's why I keep harping on it. Now, this is not the only type of wormhole solution that is found in general relativity. You also have what is called a shortcut wormhole. And this is probably, if you've encountered wormholes in movies and so forth, this is more of what you've encountered. But in a shortcut wormhole, what you have is you have a single asymptotic space, but then you have a path which can carry you from one point to another point without going through the in-between space. Okay? And I know that looks like a long cut versus a shortcut, but trust me, in certain solutions, that could definitely be a shorter path. Okay? Now, if you think about it, these are smooth geometries. These are geometries without any infinite curvature. There are no black holes here. Okay? So you might wonder, can these things exist? All right? Can these things exist? Well, it turns out, if you want to find these geometries coming from Einstein's equation, then you are going to need the energy density to be negative. That's just an essential ingredient in getting these as solutions to Einstein's equations. The problem with that is that there's nothing that exists which has a negative energy density except for quantum mechanical effects. The quantum mechanical effects are very, very small scale. So one can imagine these things existing at the scale of quantum distances, which means, of course, you can't move through it. There's no very large version of these. Okay? Now that might have seemed a bit disappointing, but watch where it takes us now. And this was the whole point of me going through this. Are there any questions before I press on? Okay. And trust me, if that picture looks weird, wait till you see the one I'm about to draw. Shit. For this one, I'm going to need a sip. That's an excellent soda pop. Thank you. All right, here we go. What metric is our best friend?
Schwarzschild.
The Schwarzschild metric, exactly. So let's consider the Schwarzschild metric. Okay? And for now, because we're using Schwarzschild coordinates, we're not going to those Eddington-Finkelstein coordinates at the moment, so we're going to use the Schwarzschild coordinates, which means going through r equals 2gm is a no-go. So we're just right now going to think of this as r is larger than 2gm. And what we're going to do now is we're going to introduce a new set of coordinates, which are going to help us explore whether or not this space is geodesically complete. We should ask that, right? Of course. So the coordinates that we're going to use are t, and just for now we're going to call these 1. T1 is going to be r over 2gm minus 1 to the 1/2 e to the r over 4gm times the sinh of t over 4gm. And the r1 is defined as, once again, r over 2gm minus 1 to the 1/2 e to the r over 4gm cosh of t over 4gm. Good. And by the way, if you wanted to get your name on anything in general relativity, you just had to write down a coordinate system. Every coordinate system's got its own name. These are called the Schwarzschild coordinates. Okay? All right. So clearly this is just a rewrite of the R and T. The angles are just going along for the ride. Nothing weird happening there. Now, since T lives from minus infinity to infinity, and R is only greater than 2gm, then we can find the range of these coordinates. T1 goes from minus infinity to infinity, and R1 goes from 0 to infinity. Okay? Now, in terms of these new coordinates, the metric is going to take the following form. ds squared is 32g cubed m cubed over r e to the minus r over 2gm. I know this is looking ugly, but watch this. Minus dt squared 1 plus dr squared 1 plus r squared d omega squared. Okay? Now, I know you might be like, why are you still got the little r in there, you know? Well, that's actually going to be useful, okay? So we'll find that useful in just a moment. But let's talk about some important aspects of these Schwarzschild coordinates, in particular by looking at this metric. So, first of all, lines of constant r, okay, satisfy t1 squared minus r1 squared equals 1 minus r over 2gm e to the r over 2gm. Okay? Well, this should kind of be obvious what that should look like. Okay, it should look like that. Where remember, this might be the equation of a hyperbola, except r is only positive. Okay, so only getting half. Okay. Well, in particular, if we take r equals 2gm, then what does this become? This becomes 0, and then what's the relationship between t and r? Well, t is plus or minus r. Okay? So we have the following. And I should now be a little bit more careful because obviously everything's asymptotic for that. We should draw something like this. Okay? So again, r is fixed, r is 0, r is 0, r is fixed. Okay, now I know that's weird, but that's just the way it works. Okay, so a curve with constant value of r is represented by this half of a hyperbola. Okay? Well, now we can ask, what about lines of constant t? Lines of constant t satisfy T1 is R1 times the hyperbolic tangent of T over 4GM. Okay? We're basically dividing these so that all the R factors disappear. Yes?
I thought we just said that R was 2GM instead of R equals 0 on the graph. We labeled the.
Oh, sorry. You're right. I apologize. You're totally right. This is 2GM. And this is 2GM. Thank you. Thank you. All right. So, oh, well, look at that. dt1 dr1 is a constant. This. So this, of course, means that a line of fixed time is just a straight line, where the slope is determined by the hyperbolic tangent of the value of t that we've selected over 4gm. Okay? Now, here's the most important observation. If we ignore any angular motion, because we're just treating this in the TR plane, what do light cones look like? What's ds squared for a light cone? Anyone? ds squared for a light cone is 0. Okay? Well, I'm taking this to be 0, and I'm not looking at angular motion. dt dr is 1. If this is equal to 0. Does everybody see that? This isn't going to be 0 in general, so these have to equal 0. But that just means that the light cones everywhere in the picture open at 45 degrees. That is not what we found in either the Schwarzschild or the Eddington-Finkelstein coordinates. There, the light cones were bending and deforming. But in this picture, light cones, anywhere I draw them, are opening at 45 degrees. So a light cone here opens up at 45 degrees. A light cone here opens up at 45 degrees. Okay? Now, clearly, there are two observations. One, is this space geodesically complete? Well, why don't I just think about the light cone coming from here? I don't have to follow light. I could just follow the path of a massive particle, but light's a super easy one because it just travels along these 45-degree cones. This guy is going from this region. Notice, everything that I've talked about is restricted to this part of this space. Okay? But clearly, a geodesic path can go through here, so we need to extend this space to what's up here. But that should be obvious. This is a black hole. This is the horizon of the black hole. You know you can go through the horizon of a black hole. Okay? Now what's beautiful is that to extend this to r less than 2gm is pretty straightforward. We define region 2. We flip these around. And then we swap these two. Okay? And then what is important is that in these coordinates, T2 now ranges from 0 to infinity, whereas R2 now ranges from minus infinity to infinity. Okay? If we write the metric in terms of these coordinates, then it's going to take the following form. Done. Were you looking down or were you looking at the board when I did that? What did I do? What did I change? In this metric, what did I change? I changed the 1 to 2. That's it. The geometry is the same. The metric is the same as in the original coordinate system. Okay? So this implies some interesting things. First of all, constant R in this case, constant R is now going to be curves in this direction. Okay? Well, there's a special value of R that we might consider in this, because, and when I say R, I mean little r. There is a special value of R which corresponds to the singularity at R equals 0. Well, that's a curve. So this we could identify as the R equals 0 singularity of the black hole. I know it's a line, but that's just the way it works out. In the capital T, capital R coordinates, the point R equals 0 gets mapped to a line. Okay? Constant T. Oh, constant T just goes like this. And light cone's still open at 45 degrees. Okay, I want to make sure that this is asymptotic. Now I want you to just look at that for a minute and think of everything it's telling us. Notice, if I start out here, I can move away from the horizon of the black hole and never go into it. Or, if I want, I can go into it. However, once I'm inside of it, where am I headed?
R equals 0?
To R equals 0. Because once I'm inside of it, all of the light cones are forcing me to move up. And that means I'm eventually going to hit R equals 0. I can't go away from R equals 0. So this picture is just reflecting a lot of these facts that we learned about black holes last time. Okay? So that's pretty useful. Also, look at this. That light cone should remind us of something special. Remember when we were talking about where we could go near a black hole? You could move in, you could move in, you could move in, or you can move out, in, and you can be at rest. Well, here you go. Here is a piece of light which is cruising in, that's this trajectory. But here is a piece of light which is sitting at the value R equals 2gm. That is this trajectory. I'm just trying to get you to identify the elements of this graph. This is a very useful graph. Look, it's not the best. R equals 0 is now a line. But what's the most valuable part about this is that the light cone's still open up at 45. Damn, that makes it easy to figure out where you can and can't go. I don't even need to draw the light cones anymore because you're just like, oh, if you're going straight up, you can go there. If you're trying to go horizontal, can't go there. Okay? So, pretty good picture, right? It does have a problem. Here's a light cone. Where does that come from? Notice the only part of this diagram where this space exists is here and here. What would you call this space? It's not geodesically complete. Okay? Now, I want to stress something to you. This light cone ends at r equals 0. This is geodesically incomplete. If you think about it, if you go back to this picture, if something is moving and it hits r equals 0, it stops. It doesn't come out the other side. So you might say, oh, a singularity is causing the space to be geodesically incomplete. Well, I'm going to turn it around. The true geodesic incompleteness of a space tells us there's a singularity. But here's the important observation. This is geodesically incomplete, but there's no singularity here. So we should complete it. Let's do it. So hopefully this is becoming obvious. This is region 1. This is region 2. I don't really need to give these labels. And now we can do a region 3. So using region 3, all we need to do is say, okay, T3 is going to be minus T2, and R3 is going to be minus R2. We're basically going to take everything as it's defined up here and define it similarly down here. And that will lead to the following shape. Okay? All of the same shit still holds. Lines of constant r are halves of a hyperbola. Lines of constant t are just these lines that come down. Okay? And the light cones still open up at 45 degrees. But notice now, that is the forward light cone. Here, the forward light cone ends at the singularity. Here, the forward light cones are born from the singularity. What might we call that?
White hole.
A white hole. Where this is a black hole, this is a white hole. And get this, a white hole has an event horizon. Right here, at r equals 2gm. But what's interesting about the event horizon is once you leave it, you can't go back. Moreover, you must leave it. You cannot stay in the white hole forever. You must leave. And when you do leave, you can't ever go back. Pretty cool, huh? Is that the end of the story? Hell yes. Hell yes. There is still a region 4. And we need it because notice, here's a light cone emerging from the white hole. This is not geodesically complete unless we have something here. So to fill this in, it's probably pretty obvious. We can take T14, this is region 1, or this is region 4, this is region 3. We can take the fourth regions T and set it equal to minus the first region's t. And we can take the fourth region's r and set it equal to minus r for the first region. Okay? And then what we're of course going to end up with is this same argument. Okay? Where in this region of space as well, light cones open at 45 degrees. Now, I want to remind you, all we did was we said, let's ask if the black hole's geometry is geodesically complete. We know it's not geodesically complete in terms of the singularity, but we want to ask about the rest of it. Okay? So the rest of it, it turns out it's not unless we maximally expand it. Now ask yourselves this for a moment. What's that for, Noy? What is this space? What is this space? Well, let me ask you this. What's this region over here, region 1? What is it?
Our regular space?
Well, yes, but there's a verb or there's an adjective I should put in front of, what is it? It's
Flat.
what is it asymptotically?
Flat.
It's flat space. Okay? Sure. What is this as I go asymptotically away from it? It's flat space. Are these the same two flat spaces? Nope. Can you get from this space to this space? Nope. These are definitely not the same copies of M4. If it was a single copy of M4, you could move from a point to a point. You cannot get from here to here. Because you have to move in the path or inside of a light cone. The light's doing the best job it can. Can light get from here to here? No. Okay? So in a sense, this is a wormhole space, but really and truthfully, the only way to get from region A to region B is to visit there. Now don't get me wrong, this allows us some interesting opportunities should this actually be the shape of space-time. Because for example, you and your sibling could be born from the white hole, right? Yeah, sure. Okay. You might decide, I'm going to go this way. And your sibling might decide, well, screw you, I'm going this way. You would get experience of this copy of M4, which has 6 Earths with 1 million playgrounds. Whereas your sibling just goes into our copy of M4, which has 1 Earth with 1 million playgrounds. Okay? But unfortunately, you can't compare notes, right? Yes, you can. How can you compare notes?
Go into the black hole.
You go into the black hole. If there's any place that something from here and here can go, I am not saying you can go from here to here or from here to here, but anything here and anything here both have the option of entering the black hole. So they get a little bit of time to swap information, to tell stories. And then it's the singularity and death. Okay? Maybe you guys are just not that excited by this kind of picture, but I am.
I have a question.
Yes, go for it.
Are white holes real?
That's an excellent question, which I'm about to supply you with the answer. Okay? Are there any other questions about this? Because that's what's on my next slide. Yes?
So is like region 1 and region 4 basically like a parallel universe in essence?
Parallel universe is a nice way to put it. Yes. Yes.
Go ahead.
If we have an infinite.
Yeah, you guys should keep asking me questions so I can drink some soda. Go for it.
Fantastic. So this may or may not stick, but it makes sense. If there's like a million more dimensions to this, because this is all in two axes. If you have like a million axes, and you keep having this repeat over and over, would that be like the infinite universes? If these are parallel universes, can you have infinite universes proving
Wait.
a similar structure?
So you're saying I've got 2 universes here. Can I make it an infinite number?
Yeah.
We'll do that later.
Really?
Yep, I don't want to do it yet. We'll do it later. Trust me, this is not the end of this story, Funny. If you think this is the end of the story, you need to get some soda. Yeah, go for it.
We talked about the wormhole jumping over spaces a little bit ago. Can a quote wormhole go from region 1 to 4? Because it would connect 2 flat spaces.
Well, actually, we're going to talk about that. So this has the unfortunate conclusion that to merge something from here and here requires death at the singularity. We will find alternative explanations, which are actually way more common, where you can actually meet from 2 different universes and not go to death at the singularity. But when I get to that picture, you'll understand why. Okay? Now, these are not standard wormholes. Standard wormholes had no singularities. That first problem that I worked out where I did the wormhole, that didn't have any singularity in it at all. Okay? That is a solution to Einstein's equations for particular negative energy density sources. These solutions are only positive energy density sources. These things could in principle actually happen because everything in the universe at the classical level is positive in its energy. Okay? By the way, sorry, I feel like I should say this now because I don't know if I can tell it to Physics 100 students yet. You know how in everything you've ever done in physics, you have learned that the absolute value of energy is irrelevant. All of physics is driven by changes in energy. So when you talk about what's the energy of a system, it's the kinetic plus the potential plus a constant. And that constant you can set to be anything you want, right? Right? You can do that everywhere in physics except in this class. Because if you have any energy, it will deform the geometry. Even a uniform energy, that will deform the geometry, that will curve the geometry. So one of the important observations is that positive energy abroad is the only acceptable solution. Okay? Unless you're doing quantum versions, because quantum effects can lend itself to negative energy contributions. Okay?
Would dark energy state?
Sorry, say it again?
Is dark energy a type of negative energy?
We will talk about dark energy at the end of the semester when we actually apply this to the entire universe. So let me hold off on answering that till we get to it. Okay? Other questions about this picture before I really dumb it down and make you go, oh, damn. I mean, I find it pretty fascinating personally, but that's okay. All right, so, let me see if there's anything else interesting that you put out.
Alex?
Yeah, I'll give you a hint.
Oh, I was just going to ask a silly question. If that was you and your brother and you guys went through a black hole to meet up?
I don't know, man. Bob, what you think? You gonna go left, you gonna go right? Are you gonna go, so we're being born from a white hole, and one of us is going left and one of us is going right into these parallel universes. Then we're gonna meet up here at the black hole singularity and compare notes for like a little bit. You go left? He's kind of left leaning. I'm left leaning as well, so I will go. We'll just go left together. Yeah. Yeah, we'll go left together. Okay. All right. So. Yeah, so I will just give you a hint, i.e. the answer to the homework. How much time do you have in order to compare your notes? And the amount of time you have is GM pi. But you will determine that on your homework. Which, if you downloaded an earlier copy of it, download a more recent copy because I kind of gave you more steps to walk through to help you, not to do more work, but to help you. Okay, so there's a couple of problems with asking whether these exist. Number one, the Schwarzschild solution. Does anyone notice anything funny about the Schwarzschild geometry? No one?
Wait, are you asking about like the geometry itself or like that d omega? Because I really don't like that d omega thing.
The geometry is described by this metric.
What if there's two black holes?
Two black holes is interesting. That's something we could talk about later, but this solution in and of itself has a fundamental problem.
Are the white holes not possible in it?
Well, that's what we're going to argue, that they're not possible in the real world. Why can't this describe the real world? There's no time dependence. Think about it. In the real world, can a black hole live forever? In the future and the past? No, our universe has a finite age. Our universe is born. It doesn't go back to t equals minus infinity. But for a time-independent geometry to be true, this solution has to hold from t equals minus infinity to t equals infinity. Okay? Moreover, realize that the black holes in our universe were not born at the Big Bang, rather they were formed from stellar collapse. So the black holes have a finite lifetime. Okay? So the black holes that we expect exist in the universe were born at a certain point. And so you might ask, how does that deform this picture? And it actually deforms it in a rather significant way. So, for a finite lifetime black hole, and trust me, I'll draw this picture once and then we'll forget about it, because these things suck. These reality checks. No, we want to live there. Okay, so what does it look like for a black hole that is born? Well, trying to do as much as we can, like what we did up there with all those lovely Schwarzschild coordinates, we have this, and then we have this, and then we have this, and then I have this. And then I have this. And this. Yes, that's it. Okay. So this guy right here is the r equals 0 singularity. This is also r equals 0. All right? This is the surface of the star, which will collapse and form a horizon. Sorry. At r equals 2 gm, or we can take this to be t goes to infinity. Okay? And we can also take this to be r equals 0, or t goes to minus infinity. Okay? But the important thing is that in these diagrams, this line also represented r equals 2 gm. Okay? If we were trying to do a similar coordinate redefinition, starting with a space that has a star, which does not have a singularity at r equals 0, okay? It's got some internal form of the metric, which it's going to be dependent on the specific scenario, but it's going to have some internal form of the metric, and then the exterior form is going to be Schwarzschild, okay? But nonetheless, we'll have the non-zero surface of the star, and then when it starts to form collapse, we will at some point have a singularity form at the center. This is before all of the mass of the star has collapsed to the singularity. A singularity will be born before all of the mass is there, okay? So the singularity will form, but eventually it will fill out the space and we'll have the horizon, okay? Now what's important about this is that this is the r equals 0 from normal asymptotically flat space. That is, you cannot go below this. All right? So this is not geodesically incomplete like it was in this picture, which is what you would expect. It does become geodesically incomplete once the singularity is formed, because you can take a path into the singularity and that ends your geodesic path. Okay? So unfortunately, these lovely things do not exist in the real world as we experience it. Now you might ask yourself, why? Why? Why do we talk about this when this is the reality? Well, here's the interesting observation. General relativity, if it is true, it should be able to accurately describe spaces like this should they exist. It describes spaces like this, obviously, but it should be applicable to even these weird, fancy spaces. And it is these weird, fancy spaces that are so simple in their construction which allows us to investigate some of the more treacherous aspects of general relativity. For example, what about when I try and quantize general relativity? Okay? Well, it turns out that this picture is essential to one of the most recent developments in the idea of general relativity in terms of quantization, and that is that our universe and its geometry is actually holographic. And in truth, we are born from a flat space upon which lives a quantum theory. And the curvature of space-time that we experience in this holographic realization is actually encoded in the entanglement of the underlying quantum theory on flat space.
Can you repeat that, please?
So the idea, and this is born from something called the Nes Cft, which some of you might have heard of and some of you might have not. Okay? But the Nes Cft Correspondence, which was born from string theory but now has its own line of research, says if I have a space called anti-de Sitter space, this is a space of constant negative curvature. We talked about this earlier. We were talking about maximally symmetric spaces. Positive constant curvature is de Sitter. Flat is Minkowski. Negative constant curvature is anti-de Sitter. But an anti-de Sitter space has a boundary. That's an interesting deviation from the de Sitter and the Minkowski. Anti-de Sitter space has a boundary. And what was discovered in the anti-de Sitter space conformal field theory correspondence is that in this space, gravity lives inside of the cylinder, whereas the boundary is a fixed geometry. And on the boundary, you describe the physics in terms of a conformal field theory. That's a quantum field theory with a special symmetry called the conformal symmetry. Okay? Here's the important thing. Anything that's happening on the boundary, you can describe in terms of what's going on in the bulk inside. Correspondingly, anything that's going on inside, you can describe by what's going on the boundary. That's why this is a correspondence. It is a holographic correspondence because the inside of this is higher dimensional than the boundary. Right? As I've drawn it, the boundary is two-dimensional, the interior is three-dimensional. But here's the more important observation. The interior to this has gravity. The exterior of it doesn't. The exterior of it is fixed. So from this correspondence, there was born the notion that gravity and the deformation of space-time could very well just be a holographic implication of a fixed geometric quantum theory. And there was a lot of questions of, okay, what about this is related to things here? And one of the most important conclusions were that the areas of things in the bulk, which is based on the deformation of the geometry. So just to heighten this example, this is something called the Ryutaki Anagi formula. But if I take a region on the boundary, say a circle that's on the boundary, and I ask, what is the entanglement? That's a quantum mechanical idea. What is the entanglement between what's inside of the loop and what's outside of the loop? Turns out if you're doing quantum field theory and you pick a region of space, whatever's in the region has to be entangled with what's outside of the region. You don't get a choice. Many of you are familiar with finite quantum systems. This is quantum field theory. It's a little more subtle. But if I just take a circle in space and I say, what's the entanglement between what's inside that circle versus what's outside, it's always non-zero. That entanglement is directly proportional to the area of a surface which goes into the bulk and shares that boundary. And this is a well-defined surface. But clearly this surface, which goes into the bulk, depends on the geometry of the bulk. So the geometry of this surface is directly related to the entanglement. That means that gravity is directly related to the entanglement. Okay? Don't worry if this isn't sinking in. This is obviously beyond this course. I just wanted to point out that this picture plays an integral role in this discussion. Okay? How are we doing? Good. I think we're done today. I will see you all on Tuesday where we will continue this craziness. Thanks for the soda pop. You guys enjoy the next few days. I know it's a break we've all needed.